Yeah, recording. Still waiting for like a third of the class to join us, and there was quite a lot of interesting questions on the uh. Okay, so many interesting questions. Go one by one. The first one is what kind of experiments are done in computer science, especially let's assume these are more of the research front, right? Is it benchmarking? Is it testing? At the end of the day, that depends on your hypothesis, right? The same thing that we learned in the science class, right? We basically we observe that okay, these behavior happen and that's bad, and we want to fix the problem, and then we develop some hypothesis to say, okay, this bad thing can happen because of X and Y and Z. And then you would design an experiment to prove your hypothesis, basically. So I'll give you one example. Hopefully it's more clear. How many people have a laptop without the GPU, but have an onboard GPU, like an Intel processor or the AMD APU? How many people have laptops like that? Like you don't have the discrete GPU. You don't buy an individual GPU. It actually comes with the CPU. So sorry. Okay, do you all see that? Awesome. Yeah, he hit some keyboard button. I'm safe. How how do I know that? So if you use MacBook, if it's not MacBook Pro, it's likely the Intel integrated graphic cards. Basically, what it is on the chip, on the CPU that you have, actually there's a GPU integrated with that. It's similar to your iPhone, for example, right? Your iPhone has the integrated GPU on it as well. Why do we need that? So that you can display things on your monitor, so you can render the YouTube video that you're watching in 1080p, right? Or even 4K for many of the more high-end integrated graphics, right? So that you don't feel like this video is going to be too jittery. You can't really listen to it or things like that, right? So this is basically my first research project that get published. I was an intern at AMD, right? And we were working on, back in the day, AMD was working on the APU, right? History lesson, back in the day, there's a company that produced a graphic cards called ATI. ATI and NVIDIA are the two major companies in the world back in the day that produced the GPU. And then AMD bought ATI, right? And one thing that kind of obviously they can try to do is to bring in the GPU technology to the chip, right? So that your chip has the CPU and the GPU, right? And my project looks into, okay, what would happen if you try to actually have the GPU integrated on chip? The GPU that's really powerful, like an actual GPU that can render games like Diablo 3, right? So I performed some experiments and it shows that one of the problem is if you don't have a discrete GPU means that you buy your own GPU and stick to your motherboard on your desktop, right? So if you don't have a discrete GPU, it turns out both the CPU and GPU share the DRAM, the memory, right? So it's something like this. So I'm going to draw it on the slides because why not, right? So you have the CPU and you have the GPU. This is on the same chip, right? So this is your chip. And then they happen to use the same DRAM. And it turns out the GPU is super demanding in terms of bandwidth. That actually most of the DRAM design for GPU would feed a lot of bandwidth to the GPU because that's how GPU is designed, right? So what would happen is if I have the system running and I play video on YouTube or I play some games, the GPU would use so much of the DRAM bandwidth to the point that the CPU is like, hey, I need to use it too, but I cannot get access to DRAM because GPU keep using that. So anyone here, let's guess what would happen if I run this. If I let them run normally without any control. The GPU basically kind of take over DRAM and CPU is like, I can't access my data. It can run out of memory. It can also run out of bandwidth. because when you look at this, right, DRAM is connected to the chip. There's actually physical wires that connect DRAM to the chip, right? And those are used to transfer electrons. And if the GPU use all those wires, the CPU is like, okay, when can I use it? Right? And it keep asking, when can I use it? And GPU say, no, I'm using it right now. And the policy in the handle who gets to use DRAM are not aware of that. So basically, my first paper looked into, okay, if you have a system like this, how do you design the scheduler to manage basically all the demand from the CPU and the GPU to make it fair without sacrificing performance, right? So what I do in terms of experiment is then I built basically we, right, the team at when I worked as an intern at AMD and myself built a simulator. It model the CPU. It also model the GPU. It model DRAM. It model this particular feature. It actually run a real program. It's a trace of a real program. When we run this, it represents basically the normal use of your machine. On the paper, we actually evaluate with like popular first-person shooting games at the time, popular. Actually, I kind of forgot what games we actually evaluated with, but it's actually is emulate those kind of game as if they're running on my GPU simulator, right? And then the data shows what we hypothesize, which is it ran out of bandwidth because the GPU keep using that. So what do? We then have the next hypothesis on how do we fix it, how do we manage the control. Basically, we would then redesign, right, the structure that control the who get to use the DRAM. And we then prove again through experiment showing that our new design is better than what currently exists in your chip, right? And then we publish. Basically, that's how you prove an idea in CS, right? You basically, when you experiment, you have to do the same experiment for different brand of component. Yes. So you have to kind of cover configuration. The beauty of simulation, right? So the word simulation, it comes from the verb simulate, right? We quote unquote fake the actual operation of the CPU. And we not fake in a sense that it's not realistic because we also test whether it's accurate or not. But it does run a real program and it does behave like a CPU and behave like a GPU. But the beauty of simulation is we can change the configuration so that it would look like a different GPU and would look like a different CPU. I can add more core. I can reduce the number of core. I can make a GPU more powerful so it becomes the future GPU in the next 5 years. I can make it less powerful so it models something close to the mobile phone, right? So those can be done depending on what points you want to prove. Basically, when you publish a good, so I had to make a sum. It should be a good paper, right? So when you want to publish a good research work, right, it should cover the general, like the most of the use cases and probably the future trend as well, right? So hopefully that answer your question. Do all the theory use when you design the GPU? To be honest, actually many of the things you learn in this class are actually a building block behind the fundamental design of the GPU, right? How you would manage the data in a GPU. How do you run things? When we go through the last set of modules, not this module, but when we talk about the cache and virtual memory, that also has to do with the GPU and the design of the GPU. I actually, to be honest, I do have a lecture video on GPU on YouTube because we don't have the time. For the interest of time, I'm not gonna expand on that too much. But if you are interested, check channel. I do have the Thai version that I gave at Chulalongkorn University. For that lecture, I cover how and how the um basically how does the memory hierarchy, the whole like CPU, the memory, the GPU, how they interact, and what are the key differences in the GPU application versus CPU applications. I also have the English version that I use for lecture at TGS, also as a lecture at WISTech for a PhD. So if you have any questions, feel free to let me know. This is basically my thesis, right? I can probably safely say that I'm one of the GPU expert in the world. So if you have questions about the GPU design, the memory design for the GPU, and also the last topic we'll learn in this class, the virtual memory design, ask me. I am I have a I am pretty sure in this country I know the most on those topics. Um, I'm sure when I'm one of the experts in the world as well. Like whenever there's a paper that I need to review, it's actually most of them are on these topics. So if you have questions, I'll be more than happy. Can we ask for building PCM? Yes. Sure. Yes, I'll be happy to. So, either Discord and tag me. I'm sorry, last week it was hectic, but I'll try my best to check Discord. I'm sorry. I know that's my bad on not checking Discord often. Um, but yes, if you want to build PC, certain things are more cost effective than others. For example, you don't need to buy a new GPU right now. Don't buy it. Wait until I guess the cryptocurrency crash, and then people mine less. Uh, so the GPU becomes normal again. It's like the price now is absurd. Like it's really absurd. Yeah. Well, not pricing, especially from the technical point of view, it actually make no sense in my opinion. And might argue that, hey, I need to do more research. I would argue again, do more research on your side about distributed computing, and see how, be honest, how inefficient certain things are, and whether there's a need for you to go there in terms of decentralizing all those uh, like controlling the how you control the money and everything, right? And again, you want to decentralize. Going side topic anyway, right? Do you know about company that basically allow you to trade this cryptocurrency? So one thing I find weird, really, really weird, is the motivation behind cryptocurrency is you want to decentralize everything because there's no central entity you can trust, right? So that's the key motivation behind the whole thing. But to actually make use of it, you need a company that trade cryptocurrency for you, which means that those companies centralize all your transactions. It makes sense, right? So if you look at things from the core, I guess core technology and with the motivation behind each, the value of each thing. That aside, I think I'm on a tangential direction for like that we talk about how do you evaluate research ideas, especially in our case, right? We are building hardware that never exists, so we need to build simulators. We also talk about the GPU, and yes, definitely agree that, and also throw away all the good regulations that should have been there. My lifetime, right? Grew up. This is my 34th, going to the 35th year of my life. I mean, my life has been through the Tom Yum Goong crisis, right? Then there's a subprime crisis. It had housing market that crashed in the US, right? It's most of the time regulation are there to prevent those kind of things. And it's actually most of the time it's for the good cause. Unless you're doing a PhD in economy or like basically macroeconomy, I don't think you're in a position to talk about like hey, we should deregulate everything. So that's my take on it, right? And who am I? I only took a few classes, like microeconomy and macroeconomy in undergrad, and that's all, right? But that's my view of my take on regulations. That actually it's good to be there. Anyway, and sorry. Um, sorry for going for tangential direction. So today, so let me erase this part in the front because it's not related to the content of our class. Again, at the beginning of this class, I asked how's the exam going. So now we have more people. I hope the exam are going well. I hope you're all done with your midterm so that we get ready for final in a few more weeks that come up, right? It's how many weeks? This is 5 weeks until the final week. Yeah, time flies. Especially with our trimester systems, it's always surprising. Time does fly too fast. Nice knot. Okay. Now I know at least your WebEx. I'm not sure what happened to your WebEx. Hopefully it doesn't crash. We'll see if you crash every single class until the end of the I guess your graduation year this semester. Oh, you always have audio issue. Oh, yeah, your friend should keep a tally. So today we'll continue about program representation and quick announcement. I'll be on vacation next Tuesday and Thursday. Basically Tuesday, Wednesday, and Thursday. I need to do 2 makeup classes. So let me ask you for this. Any day that doesn't work for sure for you. Like, what if I do a makeup Wednesday morning or Wednesday afternoon? Would that work? No, not this week. In 2 weeks. Well, next week I won't be here. The week after, yes. So you cannot. Anyone? How many? How about I send you a poll? I will send a poll. I will send a poll. We will see. So I'll try to pick the slot that works best for everyone. Right? I'll pick a slot that works best for everyone. And yeah, and then once that we will reschedule that, I'll make it official by rescheduling that on Sky. I guess Sky Plus. Sunday, can we do Sunday? I guess I can double check if I can do Saturday and Sunday. Would kill me? Anyone here would kill me if I try to do that? Or my wife, maybe, or my kid. Yeah, I'll definitely make sure I read out the question for the recording. Definitely, yeah. I learned that from from 2 semesters ago that I didn't read all the questions. Yeah, definitely. Okay, so let's go with that poll and see what they work best for everyone. All right. Now let's resume. We kind of left before the midterm with how do we represent the data, right? And we talk about logical operations, bitwise operation, as well as hex to decimal, decimal to binary, and binary operation. Now that you know the binary format, basic data representation, the next thing I need to talk about this. Now you write your program. Many people here write, right? Many people here write your first C program in this class. Yes, I'm recording right now. I think. Let me know. Yeah, I think so, right? Yes, it's recording. So many people here write your first C program this semester. Maybe your first Python program of maybe a year ago or a few semesters ago, right? But think about it, right? Computer only understand ones and zeros, so it means that we need to somehow figure what should I do to represent a program. How many programming languages are out there in the world? Can someone tell me what are the programming languages that you can use? Right, Python. What else? I guess we have to go scratch. Okay. Yeah, at least two. Okay, C sharp, C plus variation that one letter. Rust. Are you on Rust with the fun part? Java, right? Oh, okay. Yeah, it's fun. It's fun. Yeah. So these are just example of languages, right? We hold off on assembly a bit. We hold off on assembly a little bit. But now, do you notice that each program here, the way you write your code is so different? The way you write your code is going to be looking different. If you look at a Python code, and if you look at C code, if you look at Fortran, yeah, sure. If you have a programmer that can only program in C and look at the code in Java, they'll be like, what? Right? But are they all Haskell? Yeah, awesome. Are they all runnable on your computer? Why and why? Somehow, some magic happened and your computer works. It can run Python program. It can run C program. And that's a great answer with the correct compiler, right? But what does the compiler actually do to your program? So you have a program coming in, right? You feed that to a compiler, and you got what? What do you get out of it? Assembly. That's why I said hold off on assembly. So at the end of the day, right, as long as you translate your program and represent that in the assembly instruction, I'm good, right? So that's my assumption. So are we all clear on this? If I can translate an actual program that human writes in C, in Python, in Rust, in Haskell, in Fortran, I use a compiler, and somehow I get the assembly out of it. Are we all on the same page on this? It will run as long as the assembly is for that CPU. So let's now recap on what's a computer, right? Because at the end of the day, right, you have the processor that talks to the memory. That's where your program and your data resides in, right? And then there's an input and output that also interact with the memory, right? So that's kind of like the high level overview of how computer operates. You have the brain, right? Input, output. And then you have the scratch pad here, right? The scratch pad would hold every command from your input, every data from your input, and somehow the brain would process that, spit out your output. Simple as that. So as long as you can write a program and compile that into assembly, right, it would work. And the reason why assembly work is if you look back at this, this is a new key terminology for you guys, right? Instruction set architecture. Anyone here heard of this three-letter ISA before? Anyone heard about this at all? Or the M1, M2 chip? It's actually the language for the CPU. If I will, basically, I would kind of ISA to the language that the CPU understand, right? So if I want to build the CPU, how do I do that? The first thing is I need to write a law that said I can order the CPU to do X, Y, and Z. The order that I can give to the CPU are the ISA, the instruction set architecture. It dictates what can I ask my CPU to do in terms of assembly code. So some sample of that is x86, that's for Intel and AMD. You can have ARM ISA, that's for the many of your mobile chip, as well as your M1 or M2 processor in the MacBook, right? You can have the MIPS ISA. Anyone know what we use MIPS on? How many people play the PlayStation 1 and PlayStation 2? So if you play the PS2, right? Yeah, it's a long time ago. Back in the day, yeah, yes, to be fair, I run into that too. Okay, yeah, the disk doesn't boot, common problem, have nothing to do with the MIPS ISA, but it run on MIPS ISA. It's like a variation of MIPS ISA. Anyone heard of RISC-V? RISC-V is another modern ISA that's actually free and open. What it means is this is from academia. The professor that came up with the design, actually, he got a Turing Award, actually. The two were kind of like the forefather of the like modern day architecture. They now these days they were like, okay, yeah, right now you look at the ISA, what are the common ones? x86, ARM. If I want to use that, I need to pay either AMD for the x86 or pay ARM for the ARM ISA, right? That means that if I want to build a hardware company, hardware startups, I need to pay those money. Why don't I invent a new ISA? Actually, this is like more RISC-V actually has a lot of the design that follow up from MIPS ISA, right? And RISC-V a lot, like basically the whole motivation behind RISC-V is they want to make it free, completely open, completely free and extensible. So you want to build your cool new hardware, you can extend it and it would work for your machine, right? So these are some of the examples of the ISA. And if you ask like, okay, what can we do as an architect? This is one thing we can do: design a new ISA or modify and look at how to improve the computer through the language that the CPU understands. So the instruction set architecture is a list of command, right, that the computer understands. Who designs the ISA? So now let's go back to the question, then who designs the ISA? For the computer, who designs everything? Let me go back to the most simple questions. So who is the one who come up with the ISA? Human, right? Us. Are we at least on the same page that we design the ISA? What does it mean? What does it mean? Is that too rhetorical? I'm sorry. It means that we have full control over what we want the computer to be able to do. Because we design the command. We design, hey, this computer should be able to add the number together. We should apply. It should be able to divide, right? So let me ask this question. Should I also add a command that would perform matrix multiply, or should I not? Let me ask this question. Should I also add this new fancy command that is not an add, it's not a single multiply, but I want to do a matrix multiply? That's a great answer, right? Maybe, maybe not. Because maybe it's too heavy to put in the ISA. Why is that? That's a great answer, actually. I love that answer. Why is it heavy to put in the ISA? Because these are the command that if I put that in the ISA, they must be able to do it. What does it mean? It means that I need to basically make a chip that has the hardware to do matrix multiply. Do you use matrix multiply on every single program? No, right? But for the program that doesn't use the matrix multiply, I never use that part of the chip. which also means I can use that part of the chip for something else totally, right? So that's why I said this is a designer, like human, designing what goes into the ISA because it dictates how do I build my hardware, right? Because having it is not interfering with other things, but if you look at your chip, right, it comes with certain size. How big is your chip? So this is your chip. Your chip. See? How big is it? Anyone see the CPU before? Like, can someone give me a rough estimate on how big is that? Yes, every single chip comes with its own specified ISA. They need to have the ISA tied to that because it tells how do I operate the chip. Yeah, it's like maybe 2 inches by 2 inches, right? So if I have a transistor that is in a certain size, what does it mean? It means that in this limited world of 2 inches by 2 inches, I can only fit so much transistor, right? It means that for that much transistor, I need to decide what do I do with them. I need to design what do I do with them so that I get the most use out of those transistors on the chip, right? So if you read, for example, I think blog post from Linus Torvald, right? He's one of the forefather of Linux. Sometimes he would say that, hey, x86 is ISA is too bulky because it contains many of the instructions that most people would never use, right? So why we carry those with the ISA and then I need to implement it on every single chip. So that's true, right? So the design of the ISA can impact your hardware. So that's kind of like the overview of the ISA. When you see the word microarchitecture, the microarchitecture is basically the hardware that goes into your chip circuitry that would perform each of the command. We'll expand on this in the PCSA class next, not next, like in the future semester, right? This is the follow-up class. I will expand on what can we do as a designer because your microprocessor is ISA plus microarchitecture. Basically, it allows you to interface between your circuits in the computer and the software, right? And hopefully with the ISA, we don't have to talk in 0 and 1s. We can talk in assembly, which is better. Better, right? This is definitely better than 0 and 1, right? We have on that. Assembly is definitely better than 0 and 1. So that I don't have to type in 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, right? Or punch card, right? Back in the day, you used punch card to program. Now we have advanced in programming languages, right? So we have cool new languages that address the semantic gap. So the ISA also has semantic gap as well. This is the gap between your software, your application, and the ISA, right? If you look at the ISA with a large semantic gap, it means that the instruction would control the signal. Take this voltage high, take this voltage low, and then compiler would work so that the instruction would control the computer, right? It means basically that your compiler would have to do all this control for you. Or you can have a small semantic gap that I say is really close to the software itself, right? It looks almost like a high-level languages. And it allows many application-specific hardware optimization. You can build the ISA that would do matrix multiply, right? So an ISA that has a matrix multiply operation would have a small semantic gap because it's close to the software, right? You don't have to write a function to do matrix multiply anymore. You just write one instruction and you're good. It's doing matrix multiply for you. Input matrix A and B, done, right? Or you can have a large semantic gap where you would individually control a lot of things and then allowing the compiler, GCC, to work its magic for your optimization. Personally, is my personal opinion, we are going toward the age where we see large semantic gap, I say, to get it more and more benefit, because now compiler technology is really good, right? So you can do optimization through the compiler without you having to write that code on your own. You can also translate one ISA to another ISA. That's how anyone use Rosetta in the M1, M2 chip in MacBook yet? The program that allows you to run x86 software on the ARM processor. Essentially, you translate from one ISA to another. You change the semantic gap, right? This can be done in software. This can be done in hardware, if you will, right? Depending on how you implement it. And what happens if the ISA changes? The computer basically cannot understand the executable, the binary that come from it, because the assembly changed. And the assembly is as if the CPU only know how to speak in English and you go in and you talk in German. You get confused, right? I don't understand you. It's what happened when the ISA changed. The compiler would have to be re-optimized for the new ISA. Or you can do code transformation like the Rosetta software. You translate another, right? But the conclusion is this. This is the same as the side of human language, right? Not linguistic side, but the use of the language available to human. So in the ideal world, right, would it be easier for human to communicate with only one language in the world, or languages? Which one is better in the ideal world? Yeah, it's the one language for every single human being is probably more efficient, right? But for cultural reason and everything, I mean, you can argue that maybe about to say that, yeah, culture study students probably background. Yeah, for cultural reasons, right? Certain language are more expressive, and that happened to ISA too. Certain ISA are expressive for certain things they're designed to do. That's why right now we haven't approached the age with one single ISA that rule everything else yet. Because similar to the language, right? It can express things in a different efficiency. And that's why we don't have a universal language. I guess I can argue that English is a good one, right? Because we can probably survive in most country using English. Or if everyone just speak Latin, yes, that can be worse than having multiple languages, right? So who knows, right? I mean, I never speak Latin. I don't know Latin, so I know pros and cons of each languages. So I can't tell, right? I can't tell. But the language has trade-off, right? Thai language, we don't have articles. We don't have the, right? Is that more confusing or is that less confusing? Who knows, right? I'm not a linguist. So, and I'm not expert in that area, but they do have trade-off, right? But now let's study what goes into an ISA. What are the core of the ISA? So I'm gonna compare the languages that humans speak. What are the core thing that goes into a sentence? Because if you want to send a command to your friend, or talk to your friend, right? You word together into a sentence, right? So what goes into your sentence so that it has, what are the core structure of your sentence? Subject and some what? Okay, I think you've been doing CS for too long. Subject and action, like verb, right? Subject and verb, and you can have some objects as well, right? So that goes into the English set, like most languages sentence, right? Subject and verb. And the instruction in ISA follow the same logic. You have the opcode, like basically opcode, there's a actual action, right? The verb that dictates what are you supposed to do. And then there's also things like, right? That is the object or the subject. What do you do with each of the object you want to interact, right? And then they'll actually have a type to go expand on this, like instruction types. Is it compute instruction? Is it having something to do with memory? Is it branch which handle if else or for loop, right? So it has instruction types. It also has the format. The format would tell you what is an add, what is a multiply, and the register is basically a temp that you can use to store data. There's also, because we have memory, right? The processor talks to the memory, so we have to basically find a way to control the memory. They would dictate how you use the memory. What else? For completeness, you can also do things like, I want to close the program. The ISA would specify how do you do that. What signal do you send to the computer to kill everything, every single, like the entire things on Windows, right? How to handle the IO, how to handle priority between printing jobs and the game you're playing. Because which one are more important to me, to the user? The game I am playing or some PDF I was about to print and I'm waiting for it? Which one is more important? The job queue at the printer or your game that you're playing right now? The game, right? Obviously, the game is more important. So that would have more priority, right? You would dedicate more resource for it. Threat management, thermal management, bloatware I have in the background. Yeah, there's quite a lot of those as well, depending on what you install, right? Your CPU, your ISA also have the way to control power and the temperature so that you use the phone and it won't actually burn your skin, right? Or you have a desktop in outside Thailand in the summer for some weird reason, they would not burn to crisp, right? Also, no need to memorize all of this because each ISA has their own manual. The Intel x86 ISA comes with a manual where you don't have to remember it, you just need to know how to read it. So let's go into the instruction. Well, let's look at it more like a reference manual where you want to do something and you can it and see what works for you and what doesn't work for you. It's like C syntax, right? And C libraries that I want to do comparing to string. So do I use string.h? What function do I use for that? So it's a thick manual that contains every single instruction in the ISA. And what's the instruction? It's basically the most basic elements that interface between the software and the hardware. And the main component, as I said, the opcode is the verb, and the operand is the subject or the object, right? For example, I can say add R0, R1, and R2. This is basically a mock-up ISA. It is not real, right? But let's say I have an instruction called add R0, R1, and R2. It can mean that the operator, the verb is what? What am I doing? I'm adding, right? I am adding. What am I adding? What and what, right? So the subject and the object are, I add R1 and R2 together, write the result into R0, right? So basically that's the core. That's the core of our command to the computer. Say, add together, write the result back here, multiply this number and this number together, and write the results back here. Why is this okay? Because the compiler do all the magic for us to translate to these commands. All right. So we are making a huge assumption on the compiler and the languages that they'll do this task and you ended up with. Now we're gonna shift gear a little bit and talk about what happened, right? What would happen when you run a C program, right? What happened when you run a C program? So to motivate that, right? We all have been using GC, right? We translate human code in computer language and you get the binary that represent your assembly code, right? So let's take a look at this. I'm gonna do a quick pause after I show the code example. After I show the code example, which is this. We are pausing here for 10 minutes. We'll be back at 3 o'clock and we'll continue on and talk about this code. In the meantime, you can use the time to look at the code, take a break, get more coffee, or wait, negative B5, what? It's basically 5 and you got 5 as the result at the end. So it's a really, really simple program. What it does is it's assign A to be 0, assign B to be 5, and then return A plus B, which is 5. Right? That's it. That's the only thing the program is doing. We will look at the assembly code as a result of this program after the break. All right. So, yeah, that's all for before the break. We will look at what would happen after we call the command object dump -s. So when you compile a program, it's in binary, it's in the format that the computer understands, ones and zero. You can convert that back to assembly by the command obj dump -s. After you do that, this is the assembly code you see and on this. Basically, what we're gonna leave right now is that this code is this. The code up there is whatever you see down there, and we'll go one by one. We'll go one. All right. So let me do a quick pause here. All right. So we will come back in 10 minutes. And let me resume here. Assuming we are back. There's a question said, since you're on the break, task 1 is init cap for the size of memory. Yes, it's the amount of bytes that the box can hold. And if it's too small, you resize that. The key here is to make sure you can keep putting things into the magic box without getting segfault, right? The key point here is without getting segfault and without making the box amazingly big. And this technique has been the technique that you use for the magic box has been used in programming since the early dawn of time, at least a computer time, right? All right, so are we all remembering the code example here that we are about to look into? So it's A equals 0, B equals 5, and then return A plus B. All right, for the sake of my own sanity, I'll get rid of the C code now. I'll get rid of the C code and just look at this code down there. All right. Anyone here want to guess what does the top line mean? What does it say in there? What does it say? Anything that resembles the code you see? Yes, it's actually the definition of the main function. How many of you noticed there's a number 5FA in here. 5FA. Anyone notice that? So this box tells you, right, that this is where the function, the main function, resides inside your memory. In this case, it's virtual address space. We'll talk about that when you talk about virtual memory. Let's assume this is somewhere in the memory. So what is 5FA for? Why is that 5FA? Anyone want to take a guess? Because we said every single function when you run is being copied to the main memory. So what should the 5FA be? What should this number be? This is the address, actually. It's the address of your main function. So if you go and dereference 5FA, you get the main function. That's where the main function is located in the main memory. All right, we are on the same page. Basically, the main function starts at 5FA. Now, the next thing, oh, it is hex, yeah, hexadecimal number. I'm sorry about that. It's hex number. Everything here you see in hexadecimal number. All right. So you see things to the left here that start with 5FA. Anyone want to take a guess? What are they? What do they stand for? Why are there numbers here? The address, yes, it's address again, and it has something to do with the line, right? Because there's multiple line to the right side over here, right? You notice that there's multiple assembly lines in here that you have to run. And how do you run a program? Is it from top to bottom? Yes, it basically run from top to bottom, except when you have the if else or for loop. That would make you loop around, right? But by default, it goes top to bottom. So if the first line is at address 5FA, the second line in this case is what address? So this is at 5FA. Where can I find this line? Where can I find the hexadecimal binary that represent this command? Move %RSP %RBP. 5FB. How about this line? 5F actually, because if you look at this third line start at 5FE, we'll talk about why does it skip. Why does it skip in a bit, right? But the left side is where, in terms of the address, where does the assembly code for each of these lines located at? Now, you might be questioning, why do I jump from 5FB directly to 5FC? Because this. Anyone want to take a guess? What is the number here in the hexadecimal digit that seems like having no meaning? These are the actual bits that represent each instruction. So 5 here is basically push %RBP. Why? Just simply because your computer doesn't understand English, so it doesn't really understand push RBP. What is that? I don't know. I only know it's hexadecimal 5. Oh, I know what to do with that, right? So what does move RSP RBP looks like in hexadecimal number? For this particular command, move RSP RBP, what is the hexadecimal number that represents these exact command? If I said this is actually 5, how about the next line? what is the binary? Yes, thank you. So this is going to be 4-8, followed by 8-9, followed by E5. So how many people here wondering then why does the first one push RBP only 1 byte? The second one, why is it 3 bytes long? 4889E3, that's 3 bytes long. Anyone having that question in mind right now? How can I tell how many bytes is there? How many people basically confused on why is it, what is push in here? Push, sorry. We'll talk about what does each of the command do in a lecture actually. But what push do is it push the value at RBP. So it push the value of RBP on the stack. We'll expand on that a little bit. So basically, these are the commands that everything combined follow that int a equals 0, b equals 5, return a plus b, the C code that you see in the beginning, right? But because the move command here is a little bit more complicated than the push command, there's no way I can fit that within 1 byte. So the Intel x86 basically say that for this command, I'm going to use 3 bytes for it. So in the ISA, it would explain how do you read each of the bytes in detail, right? So that if I want to take the ISA and build the CPU out of that, I can. So the box here shows the actual bit that represent each instruction. For example, the next line is going to be C745 F8 0 0 0 0 0 0 0 0. Right? So now do you see how many bytes is the first command? The push. This is 1 byte, right? The move actually is 3 bytes. So if push start at 5FA, I need 1 byte for the push command. So where can I find the next command? 5FB, right? But 5FB is the move command. The move command contains 3 bytes long. So if I look at 5FC, 5FC is basically this number 85. So that's still the part of the move command. How do I go to the next line? What's the starting point, starting address of the next command? It's actually not 5FC, but 5FE, right? Because we need to go 3 bytes. Then the next command is how many bytes here? The third line, how many bytes is the move L command? 7, right? So this is 7 bytes. So the next line, where can I find the next line in the DRAM, in the address? What's the address for the next line? Now I am at 5FE, and then you add 8 bytes to it. So it should be 605, right? And then again, you add 7 because the next command is also 7 bytes. You can find the next command at 60C. Then you add 3 bytes to find the next command at 60F, and so on and so forth, right? So that's how you can read the left side of this. And for these pattern, anything that you see here, these pattern, you can find what it means in the Intel x86 manual. It would basically say, if you see these bit pattern, it means this command. All right, are we all on the same page? Basically, if you see the pattern, what? I guess this C3. If you see this pattern C3, that's return kill. That's equivalent to the return kill command. So in the manual, it would explicitly say, how do I read this binary and how do I convert it back to the assembly? And then what does the assembly actually do? It would explain everything. All right. That's why I said you don't have to remember it. As long as there's a manual, you can download, and that's everywhere, right? You can download it from the Intel website. All right. Then the box I just show here is the actual instruction, not the bits, actual instruction that represent, I want to add the two number inside the register EDX and EAX. I want to add the two number together and write the results into EAX. Again, this is explained in the manual, and we'll go over what does the command actually mean in the next lecture. All right. Now I want to show the example of what would happen when you look at assembly and what does it actually mean for each of these numbers that you see. These are the actual bit that represent the add EDX EAX. If you see this bit pattern, it means add EDX EAX, right? So without this assumption, basically it means that as long as the compiler, can get your code to here, I can use the ISA manual to convert the code back to the binary, which means your computer can now run. All right. So any questions so far? Any questions so far? So if there's no questions, now let's categorize the different command we can talk to the computer. Generically, the most three common types are compute, add, subtract, multiply, and or anything that has to do with modifying the data. It performs the actual computation. There's memory instruction that moves the data in and out of the memory, right? So that the processor can process your instruction. Then there's a control instruction. This dictates what's the next line. If there's a for loop, if there's an if else, how do you go to the if or how do you go to the else? So there are basically three main types of instruction. And each instruction, as I said, there's an opcode, right? So these are the opcode, the verb in the sentence, the operation that you actually do. These are the opcode. It tells what does the instruction supposed to do. So anyone wanted to guess what does add do? Add, yeah. How about return Q? RETQ? It returned from a function call, right? So the computer would do certain things. Push and pops has to do with the stack. We'll go over that in a bit. Move would move the value from one place to another. No op means no operations, depending on how you define it, right? So the last one, just ignore it for now because it's actually beyond the scope of the class in this semester. This is basically how to, what is the place in this context? What do you mean? What is the place in this context? Oh, you mean for the move instruction, right? It can be I move from one location in the memory to another, right? I can move from one location in the main memory to another. I can move the data in the memory to my register. We'll talk about register in a bit, but these are temp variable. Basically, yeah, you can move from memory to memory, memory to CPU, CPU to memory, and CPU to CPU. Basically, it's moving the data around. Is it more clear? It allow the command allow you to moving the data from one place to another. And here is the operand, right? Basically it tells for the data that involved in the opcodes, where are they located? Is this also a part with the data res? No. Data res is a concept for the case where you want to access the same data from two different entities that can run in parallel. Right. So if you wanted me to talk about that, what can I do? Can you remind me after we cover virtual molecular last topic in this class, if we have some room, I can talk about the data race and like parallel programming a little bit. But once you convert everything to assembly, we assume your code is correct. If there's a bug about the data race, it would happen. Basically, once everything is compiled, the compiler would, in most cases, it would basically do what you wrote. But for a fancy compiler, sometimes they can detect data race and give you warning. All right. But from the hardware point of view, because we just take the command and run it, we don't have a way to detect that. Basically, just run from your program. So the place where you fix the data race most of the time is in your program. Once you know, okay, that part has a bug, if I run that program, it would literally run what I program, right? And you're gonna run into data race, or if you have a bug that causes seg fault, your assembly code will cause seg fault. It would actually try to run it, and then the OS say, hey, seg fault, stop running. All right. It would basically just directly read your code and do whatever you're telling them to do once it's in assembly. Now, there's also an address. This is a value. My bad. I circled a value. This is an address. So this box is the data that you want to load into a target. So now, remember our code is int a equals 0. So you are loading the value 0 into some location. So that's an address. That's an address in DRAM. So basically, you put the number 0 somewhere in DRAM. This is basically the offset that has to do with where in DRAM you are loading to, right? So this is basically, we'll cover this on assembly part 3 on why is it -8 plus RBP. So don't worry about what is this. It just say, I just want to say, hey, some of these are the address, some of these are the value. And the operands, right? For example, RBP, they are the operands, they are register that involved in the instruction. So now I talk about the register. Register is essentially a really fast temp variable that the CPU can access and use. Oh, what's the difference between move and move out? Move, right? Move this instruction and move out. So let me actually open up the manual so I can show you what can you do. All right, let me share my screen here. Do you see my screen? So I just searched Intel x86 manual, right? This one contains multiple volumes. As you can guess, there's many things in there. 23.7 megabytes, that's quite a lot. So let's see what's in there. So when you open up the manual, don't be discouraged by how thick it is. I'm not asking to remember any of this. It's 4,800 pages. No one remember everything here. All right, no one remember everything here. But what can you do? Move, you search, right? Move instruction. And then if you keep searching, there'll be an explanation of what is a move here. There'll be a more detailed come on. I know it's a while until we can find what I want to show you. So here, for example, this is LMSW, load machine status word. It would actually say, these are the description, load source code from here to here. These are the opcodes. And it would explain a lot of details. I'm still trying to find the move command. Here, move, right? Description of the move, copy the second operand the second operand, for example, move something here, RI is a register, right? So sorry, I know it looks intimidating and I know it looks long. It explains the different version of the move command, because move can move from memory to memory, memory to CPU, CPU to memory. And then it works with multiple formatting, right? So it has multiple version of the move command. But if you break it down, there's the first thing and the second thing. The first operand and the second operand. What it does is it copy the second operand to the first operand. That's it. That's what the move do. All right. Are we on the same page? Move, copy the second thing to the to the first thing. Copy the second thing into the first thing. That's it. That's it. The formatting can work differently for each version of the move. Now let's see move out. Right? Move out. Move out. I don't want condition move. Okay, I guess I can do this. Okay, before I am overwhelmed, let me get back to you afterward, right? I want to make sure I know exactly the move out formatting, because it is long. And even though I use this quite a bit, I cannot search on the spot. No, you don't look anything in here. Everything, the reference, I'm gonna give it to you for anything that you need on the exam. It's gonna be a lot more simple. This is x86 full-blown manual. So that's actually a long manual, because x86 cover many fancy instructions. Yes, you cannot find a move out that we want. There's a condition move if it's less than. Okay. So move double precision. I'm sure that's not what we want. Yeah, still a lot more to go. So let me go back to the slides. I'll get back to you, right? But what it does, right? Okay, share here. What it does is it moves the value, the immediate here. We call this immediate, into this location. This is an address. Immediate are value. And as you can see, these are the value. What is this? 0, right? This is the constant that we can put into our assembly instruction. Let's say I'm going to move the value 0 to this location. What's this? Value 5. Basically, I want to move the value 5 to this location. I want to put the value 5 to this address. So that's what the move out supposed to do. I want to copy the content, put 0 in here, put 5 in here. Are you all good? All right. Yeah, sorry, I want to show you the manual. It turns out to be way longer and kind of surprise everyone. Register. So we talk about register, those RBP, EX, EDX. What are those? Those are really fast temporary unit of storage inside the CPU. that directly accessible by the CPU. Think of it as a temp variable. Great question. You ask, is this L1 cache? No, this is faster than L1 cache. So if you look at L1 cache, right, these are typically 3 to 4 CPU cycle to access. For your register, this take 1 cycle. This is really fast. How much space does it usually have? Great question. It's limited. Most of the time, depending on the ISA. Now, again, you can design an ISA with 8 register. You can design an ISA with 16 register. If you look at x86, there are 16 of those. So you think of it as your program has temp1, temp2, temp3, temp4, up to temp16 that you can use. Right? This is inside the core. This is inside the CPU itself. This is inside the CPU core itself. L1 is outside but on the same chip. So again, if I draw the computer chip, right? This is your chip that you buy, the 2" by 2". There's the core, the CPU, right? And each one of them would have the L1 close by that you can access. And then there'll be the bigger level 2 cache. And most CPU nowadays also have the bigger level 3 cache, right? So yeah, think of these as a temp variable. It doesn't really store that many value, but you need it so that you can add 2 things together quickly, to multiply 2 things together quickly. The compute instruction would directly access the value that's stored in there, right? And the group of register available to the CPU, we call this register file, is the terminology that every time you see this word register file, it means these are all the register that I have on my CPU. All right. So what are the difference? Register is extremely fast. Oh, yeah, sure. Yes. So the question is, can I explain what the levels are? We will talk about that in detail when we talk about caching. But when you buy the CPU, let's say you go and buy the CPU, right? They'll come with some spec, right? Specification. So what are the common things that they will list when you buy a CPU? How many people buy a CPU before? Can you help me tell what are the things that they show on the specification? The gigahertz, right? The clock speed. Whatever gigahertz that you see, right? What else? Number of cores, right? What else? The size of the caches, right? So why cache? Yeah, power consumption, that's also another big thing, right? Is it 65 watts, 90 watts, right? So each one of them would require different power supply. But register is really fast. Memory, your DRAM is really slow. 12 to 50 nanosecond in the CPU cycle. So let's say I have a 3.3 gigahertz clock, right? How many cycles is 50 nanosecond? How many cycles is that? So in the 3.3 gigahertz clock, right, is 10 over 3.3 per nanosecond for the number of cycles. So it's 3 cycles per nanosecond. You have 50 nanosecond. How many cycles is that? It's 50 multiplied by 3. So this is 150 cycle. If you want to access the register file, it takes 1 cycle. If you want to access something in the memory, it can take from 36 to 150 cycle and more. Which one is faster? Which one is faster, the register or the memory? the register is a lot faster, right? It's definitely a lot faster. And how many people notice that there's a big gap here? If I don't use the register, I have to spend 150 cycle. That's a long time, right? That's a long time in the CPU world. So here's what I propose. I can have my data in the register, right? This one cycle. If it's not there, I can go to the cache. It's a fast memory. It's faster than your DRAM that you buy. These are inside your CPU. The first level of the cache, it takes most of the time is 3 to 4 cycles to access, to get the data in the L1 cache. It would take 3 to 4 cycles. For the L2 cache, it can take like 9 to 10 cycles. For the L3 cache, it can take like maybe 10 to 15 to 20 cycles, right? That's better than going to DRAM, right? We all agree that that's better than going all the way to DRAM. So that's why that's level 1, level 2, and level 3. Level 1 is the smallest. Level 2 is bigger. There's more chance that your data might be there. Level 3 is the biggest. It's still a lot smaller than your DRAM, but there's a good chance it's there, right? And for most of the program that you run nowadays, between 70 to 80 to 90% of the time is within these caches, right? Unless you talk big data application and many other like really, really big application. So hopefully this explained the question on what does the L1, L2, and L3 are, and why do I need the register so that you can go through the add to multiply really, really quickly. All right. The next thing is what we call a program counter. These are the special register. It points to the current line that I'm running. Why is that the case? So if you go back to these particular example, right? How can I tell what line am I running? From the computer point of view, how can I tell what line I'm running? Like if I stop time, if I have a magic, I can stop time. I stop the time right now. How can I tell what line am I on? What do you have to store in here? So let's say I want to be able to tell that right now I am on this line. I am on this line. So what is the one single value? Yes, the 5FA, 5FB, 5FE thing. So let's say I want to be able to tell, hey, I'm on this line. That address is what? What's this line? What's the address for this line? 6OF, right? So your program counter will store 6OF. It basically allows you to tell, okay, I am on this line. And if I want to proceed, I'm going to go to what? What's the next line? So if I want to run the next line, I finished the move instruction, and now I want to do the add instruction. What is the new value in my program counter? 612. And that's it. That's how I can keep track of what line am I running and how do I proceed to my program with the program counter. Sometimes if you look at old textbook, there's also a different name for the program counter. We call this instruction pointer. Same meaning, it points at the instruction you're on. It allows you to tell I'm on here so that the next, once I'm done with this instruction, I go next on the next line. All right. So that's it for what I want to cover today. Well, that's all. That's all for the things I want to cover today. Now, before we leave today, there's a new in-class exercise. As I promised, midterm week, no in-class, but now that we cover logical operation, that's in class 8. I know there's 20 minutes left. It's not a lot, but in class 8 is really, really easy. So let me explain what it is. So it takes in the input data. Input data can be whatever number it is, right? You convert your data into binary. So let me actually pull up the assignment. Give me 1 second so I can pull it up, and you can see the in-class exercise. That's actually really, really, really easy. So do you see my screen? So it takes in an integer, right? It takes in an integer. Your data is an integer. So let's say an integer is, give me some random number. 5, okay. What is 5 in binary? 101, right? The parity check will check the number of ones in your number. So in this case, how many of the ones are in the number 5? There's 2 ones, right? So the parity, if it's even, you return 0. If it's odd, you return 1. If it's even, you return 0. If it's odd, you return 1. Let's try another number. 17. So what's 17 in binary? Let's actually let's do 19. 17 has a parity of 0, so let's do 19. This is 1 0 0 1 1, right? There are how many ones in here? How many of the ones in here? 3. So the parity is 1. Now you might be questioning like why what am I doing with this, right? Parity check is actually really, really important in error checking. It's actually important in error checking, especially when we want to communicate between a computer from one computer into another computer. You can use this technique to check if there's some random error in your data or not. You add the parity bit. You add this like this parity information to your data, and if it doesn't match, it means that your data is not the same. So it means there's an error in your data. What I want you to do is to write a simple function that takes in an integer and check return, basically return the parity bits for that number. So if the number is 5, 5 is 101. There are 2 ones, so return 0. If it's 19, 19 is 1011. There's 3 ones, so return 1. If it's number 8, so that's the thing. That's the thing. Think about it. You don't actually, as I said, integer is represented in what format in your computer already. When you want to represent an integer, what is actually, how do the computer store the data, the value? Hint, hint. Use binary operation on integer because it's already being stored in the binary format in computer. Use this thing on your number. So that's the hint, right? So if you're still stuck, this will be, yeah, I'm recording, right? So it should be in a video. So if you're still stuck, we'll cover that on how do we do this in the in-class on Thursday, all right? But now I'm gonna leave you 15 minutes for this particular task. Yeah, you basically count the number ones after you convert to binary, essentially. Yeah, so we count the number ones in your binary that are represented by your integer. I'm gonna go to Discord. In the last 15 minutes, feel free to basically ask any questions. I'll come back and we'll talk about this in class exercise, all right? So let me first quickly save this annotated slides. And then I'm going to switch over to Discord. And we have 15 minutes on this particular exercise, so let's use the time for that.